Hi class. So now this is part 2 of our solving exponential word problems with log and natural log notes. So first of all, I want you to take a look at our equations that I have here, and you'll notice that the first three, sorry, that was supposed to be yellow. The first three are very similar to what we were working on in part 1. The last three now are all problems that use E, which was introduced in our part 1 notes, and we're going to use it more here. These are all problems where something grows continuously, it decays continuously, it compounds continuously. And notice the parts of the equation. There's always my initial amount, P sub 0, by the way, N sub 0. Sub 0 just means the very initial amount that you have. And then times E. And notice our exponents are the rate times the time. I'm not concerned about this rate being negative. We'll talk a little bit more about that when I do half-life. So it's the same setup in all three of those. So I don't want you to worry about which equation am I supposed to use. It's always your amount equals your initial amount, E to the rate times time. So let me go back to my pen. I'm going to skip the first one. The first example is more like a do now. It's what we were doing in part 1. So you can do this problem for practice and check your answers in the filled in notes. But let's go down a little bit and look at how we're going to be utilizing log and natural log to solve our equations. For equations with a base to an exponent, in other words, there's no E, we're going to use log. We're going to take the log of both sides and use the power rule to slide the exponent in front of the base. We've already done this. We did this when we were solving log equations. So let's take a look at example 2. I'm going to take the log of both sides. The whole reason I'm taking the log of both sides is because of the power rule. The power rule allows me to drop the t down in front. So I get log of 0.5 equals t times log of 0.75. Well, log of 0.75 is just a number. So to get it away from my variable t, I'm going to divide both sides by log of 0.75. And then on my calculator, I'm going to do the log of 0.5 divided by the log of 0.75. And I believe you get 2.41 for that answer. So for equations that contain an E, this is where we're going to use our natural log. Now, natural log is how it's pronounced, but the abbreviation is ln. So natural log cancels E. So natural log of E, for example, equals 1. Very much like 1/2 times 2 equals 1. They just kind of cancel each other out. So let's see how we're going to use those. When we have equations like example 3, you and I are going to take the natural log of both sides. So what I do the left side, I do the right side. And the power rule allows me to drop that exponent down in front of the natural log. So I really have negative 0.052 t times the natural log of e. But the natural log of e is canceling to 1. So it's nicely going away. And then you and I are going to divide both sides by this coefficient on the t. And when I do that, I get 9.823. So if you're using the classroom calculator, you have to put in the 0.6 first, and the natural log button's at the top of your calculator. If you're using the navy blue one, your natural log is on the left side of your calculator, and then you're going to do the natural log first, and then you're going to put your 0.6. Make sure you close parentheses before you divide by the denominator. So let's look at this in action. Alex is putting his money into an investment fund with interest compounded daily. That is 365 days a year. The rate, if I move it 2 places, is 0.024. In how many years will Alex double his initial investment So in how many years will he have $2,000? So my equation, the amount I want is 2,000 equals, looking at my equations up above, equals $1,000 for my initial investment, 1 plus my rate, 0.024, divided by 365, to 365 times my time, which I don't know. So this problem is different than all the ones we did in part 1 because my t, my variable, is an exponent. I need to solve for t. So to do that, first of all, I need to get rid of this 1,000 in front. I'm going to divide this side by 1,000. And I'm always going to get 2 in a doubling problem because it'll be like 600 and 300 or 1,000 and 500, or this was 2,000 and 1,000. And obviously I'm going to get a 2 when I divide it over. Equals my 1 plus 0.024 over 365. I'm sorry. I don't know why I wrote that there. 365 days in a year. Times to the 365 t power. So this is where there's no e here, so I'm going to use log of both sides. And I do that so I can put the 365t down in front. So I'm going to write log of 2 equals 365 times t times log of 1 plus 0.024 over 365. So when I'm looking at this, this is 365, sorry, I'm supposed to be on a highlighter there. Let me try it again. This is 365 times t times log of this. Now, log of that is just a number. So these are just two numbers times t. So if I want to solve for t, I'm just going to divide those two numbers. Oh, now I need to go back away from my highlighter. I need to divide those two numbers away on both sides. Give me a moment to write it all. So I'm going to divide the other side by 365 times log of 1 plus 0.024 divided by 365. So the 365 is canceling, the log is canceling, I'm getting t on that side. Now, to do the right side on my calculator, you do have to be careful about how you enter this for sure, especially in the classroom calculator. But there's two things in this denominator. So my personal preference is to divide by everything in the denominator. If I'm on the navy blue calculator, for example, if I'm on the navy blue calculator, I'm going to do my log of 2, divide by 365, divide by, I'm going to open log, I'm going to type everything you see there, close log, and hit equals. I am not going to use times in the denominator. You can't do that unless you're going to put parentheses around the entire denominator, or else you're going to get the wrong answer. So I just use division twice. But again, it's a personal preference. It's fine. This is a little trickier on the classroom calculator. If you're using the classroom calculator and you're absent for this, I'd recommend you come by where I can watch you key it in to see if there's getting any mistakes. You basically start with the log of 2, and then you're going to hit equals before you divide by 365. Then you're going to hit equals again before you divide by. You're going to do all your parentheses first, utilizing parentheses. Then you use log, hit equals, and you should get the right answer. But like I said, it's very touchy on the classroom calculator. If you do it correctly, you should be getting 28.88 years. And that's just 28 years in some portion of months. 0.88 parts of a year is what that's telling me. So that should be my answer if I put it in correctly. Let's take a look at number 5. Number 5, a boulder is under a waterfall at Yosemite, and its original mass was 3,000 kilograms. Over the past 10 years, the water has continuously, it's going to be an E problem, worn the boulder down to half of its mass, so it's going to be 1,500. At what R is the waterfall continuously dissolving the boulder? So let's try to write this. This is an E equation. So using the equations above, the amount I'm going to have is equal to my initial amount, 3,000. Actually, the amount I'm going to have is 1,500. Let me just put the 1,500. The amount I want to have is the 1,500, and the original amount I had was the 3,000. E to the rate I don't know times my time, which was the 10 years. So now I'm going to start this by isolating my E term. So I'm going to divide both sides by 3,000. And I'm not surprised my left side equals 0.5. This boulder was worn down to half its mass. It makes sense that it's going to be equal to 1/2 when I divide the 3,000 over E. I'm going to write this as 10R. So now since I have an E, this is where I'm going to use my natural log of both sides. By doing that, I get to drop the 10R down in front. So I get natural log of 0.5 equals 10R, natural log of E, which is canceling to 1. We're going to divide both sides by 10. Hopefully you don't have any issues putting that into your calculator. And when you do that, I get negative 0.0693. And I'm not really surprised to get that for my rate because this is a decaying boulder. This R equals negative 0.0693. If I move that 2 places, this means that this is decreasing in size by a rate of 6.93%. Let's take a look at the page. So this first problem says since January of 2022, the population of Townsville has grown according to this mathematical model, where X is the number of years since January 2022. So the 720,500 represents the original population at time 0. The original population is the population increasing or decreasing? Well, I look at this rate and it's more than 1. Oops, sorry. It's more than 1, so it's increasing. And in fact, I know it's increasing by 5%, because that's 1 plus 0.05. What will the population be in 2031? So 2031 is how many years after 2022? So that's going to be 9 years. So I'm going to put a 9 in for my X, my time. So the population in 9 years equals 720,000 times 1.05 to the 9th power. You can plug that in your calculator. I think we're getting like 1,117,732 if you round up, or 31 if you don't round. So it's the nearest whole person. Probably should be 31, nearest whole person. So in what year will the population be 950,000? So I want it to equal 950,000. That's what I want my amount to be. My original was the 720,000. My rate is 1.05, and I'm going to go ahead and use a t, but you could use x. So my variable in this problem is now my exponent, which we all know I'm going to need to get out of being an exponent by using my log skills. But first I'm going to isolate my base to the power of t by dividing both sides by 720,000. So on this side, it's canceling, and I'll divide in a little bit. So this is where I want to take the log of both sides. I'm going to take a log of the left side and log of the right side, and that allows me to drop my t down in front. So this is really log of 950,000 divided by 720,000 equals t times log of 1.05. So to solve for t, I'm going to divide both sides by log of 1.05. Now, if you're out there going, oh, I wonder, do the logs cancel? No, absolutely not. It's just like square roots don't cancel in that sense as well. I'm actually going to do this entire problem in my numerator, hit equals on my calculator, and then I'm going to divide by the log of 1.05. Give it a try. If you're putting it in correctly, you should get something around 5.68 years. So that's 5 years and 0.68 of another year. So that would be a certain number of months. So let's take a look at the next problem. So in Nigeria, deforestation is occurring at a rate of about 5.2% a year. So that is 0.052 as a decimal. Assuming the amount of forest remaining is determined by this function, f equals f of 0, that's the initial amount, e to the negative 0.052, that's my rate. Notice it's negative. This is deforestation, so my forests are getting smaller. It makes sense to me that my rate would be a negative rate because my forests are decreasing in size. They are not growing in size, times the time that have elapsed. So f of 0 is that present amount of forest land. In how many years, so t, where there'll be only 50% of the forest land remaining. So I actually don't know how much is there now. Like, I don't have f of 0. No one told me how many acres. Normally forests are measured in acres. No one told me how many acres I have. But I do know that I want the final amount to be half of my original amount. So I'm going to write my final amount as 0.5 times however much is really there equals how much is already there, like at the beginning, times e to the negative 0.052t. I'm going to divide both sides by the original amount to isolate my e term. And when I do that, I get 0.5 equals e to the negative 0.052t. So since I have an e, this is where you and I are going to take the natural log of both sides. And, sorry, that was just the natural log of e. I don't know why I drew that out there. The natural log of just the e. And that allows me to drop my exponent down in front. So I have natural log of 0.5 equals negative 0.052t times natural log of e, which we know cancels to 1. And to solve for t, I'm going to divide both sides by this negative 0.052. And when I put that into my calculator, I get 13.33 approximately years. That's how long it's going to take my forest land that they have to be about half of what they currently have. So let's look at my half-life problem. So half-life problems can be done a couple ways. The way I'm going to show you has 2 steps. I'm doing those 2 steps because for step 1, you and I are going to be figuring out the decay constant. We are going to find the decay constant. We're going to be figuring out how this substance is, constant. We're going to find how this substance is decreasing. And we're going to use the half-life to help me figure that out. And then after I know that, in step 2, you and I are going to use the decay constant. So we're going to use the decay constant found in step 1 to answer the question. So let's see what the question says. A certain element has a half-life of 1,500 years. So it decays to half the amount in 1,500 years. So however much you start with, you're going to have half that amount in 1,500 years. So how long will it take 20 grams to decay to 12 grams? So one of the ways to do this is to find that rate. How is this decaying? So to do that, if we think about the half-life, you could start with a 0.5. So people do this 2 ways. They say that the amount remaining is going to be half the original. So half equals 1 times e to the negative k, because it's decaying, so it's negative, times 1,500. This is that last equation on the last page. And sometimes people use 1 and 2. So like they'll use like 1 equals 2 e to the negative k to the times the time, which is 1,500 years. So either way, over here, before I get started, I'm going to divide both sides by 2. you and I are going to end up with the exact same equation. The point is that half my mass is decaying away. So I'm going to go back to the first one I wrote. I'm going to do the natural log of both sides. So the natural log of the left side and the one I'm not worried about, so divide the one away, and the natural log of the other side. And I get, when I drop my exponent down in front, I get the natural log of 0.5 equals negative. I'm going to write it as 1500 if that's okay. I like the number in front of my variable. Natural log times e, which we know cancels to 1. So now I'm going to divide both sides by negative 1500. And reminder, it's negative because this is a decaying half-life problem. So when I divide that on my calculator, my k equals a long decimal. And I'm going to keep a bunch of the decimal places. 0, 0, 0, 4, 6, 2, 0, 9, 8. I'm going to keep a bunch of the numbers because I'm going to use this in another problem. The more decimals I have, the more accurate my next answer is going to be. So now let's do the second part. We're going to figure out how long it takes 20 grams. This is the original amount to decay to 12 grams. So I'm trying to find how long it takes this original 20 to decay down to 12. E, and now I'm going to put in my K, my negative 0.00462098 times time. I'm trying to find how much time does it take for 20 grams to go down to 12. So before I can do the natural log of both sides, I'm going to isolate my E term by dividing both sides by 20. And then I get 12 divided by 20 equals this e to the negative 0.004. Isn't there a third zero? You know what? Go add another zero up there. Go add a zero down here. So many numbers to be careful with. 462,098t. So this is where we're going to do natural log of both sides. And that allows me to bring my exponent down in front. So I get natural log of 12 divided by 20 equals negative 0.0046298 t times natural log of e, which we all know is canceling to 1. So now I'm going to divide by that decimal on both sides. So many little digits to write. Cancels, it cancels. And if I'm careful and I've kept all my digits correct, I should be getting around 1,105.4 years for it to decay from 20 grams to 12 grams. Thank you so much for watching this video. I'm hoping it was helpful to you, and I will see you in class. Thanks.